So, we had seen that a formula is satisfiable if and only if its SCNF is satisfiable. Our aim was to extend resolution method from propositional logic to first order logic. Now, let us see how the resolution process goes, and then whatever we need we will have to introduce. Okay. So, suppose we start with these clauses. Say I have one clause having Px and say not Qx or say not Qy, fine, this is one clause. So, that means we will be writing it as and or which one? It is a clause now. So, the formula is in SCNF. So, it will be written as and or. We are taking a clause. Each clause will have or. So, let us take Px and not Qy. We will take or here. Okay, this is one clause. Suppose I have another clause which is say Qy. Okay, and another clause which is simply Px. Fine. So, this might have come from one entailment, one consequence, like for each x, each y, Qy implies Px. Okay. Similarly, you can say this is for each y Qy, and then on the right side you have entails, you want Px. So, it will be in the form there is x not Px, some such thing. Okay. Then when you use reductio ad absurdum, bring it to the other side, that becomes for all, and then you have Px, right. Okay. Now, it is easy to apply resolution on this. You can just take this clause plus this clause and you have negation of this, negation of this. So, you take just Px, right. Then that is all it will say, nowhere it will move after this, fine. Suppose you have not Px here, then of course you can use this and reduce it to bottom. That will be a resolution refutation of the clause set. Okay. So, when you take set, that means this is a clause and this another clause and the other clause, just like your PL formalism. SCNF is that. Okay. Is that clear? It looks we can extend, that is what it says, but let us hurry through. See another argument. For example, you have say all men are mortal. So, that you would write as say mx implies some dx for each x, right. So, which will give rise to the clause not mx or dx. Okay. Then you have another, say Socrates is a man. So, you would write m s, s is a constant now, fine, from which you want to conclude that Socrates is mortal. So, that will be ds. Okay. So, now in this side you have the clause set as not mx or dx, then another clause is ms, okay, and using reductio ad absurdum not ds will go to the premises set, right. So, you have not ds. Now, there should be a refutation of this, that is what we feel. Okay. So, first thing is how to conclude from not mx and ms, they should resolve, fine, they should resolve and we should get something like ds here. Okay. So, this step we are not convinced, but something has to be done. Then from these two steps you would get a refutation. Okay. But what does this step means? It really corresponds to the argument here. For each x, mx implies dx, ms therefore ds. That is what being inferred here. That should be correct, but we do not know how to tackle that in the resolution process if you just follow the PL formalism, fine. So, somehow from each x we have to go for any particular s. All that we see is x has become substituted by S. So, substitutions we have to take care now, right. Moreover, we want this to be done by a machine, not always looking at it and finding the appropriate substitution. So, machine should be able to find out what should be the suitable substitution there, right. So, now our responsibility is to formalize this part, how mechanically it can be done. Okay. So, for that purpose let us start studying the substitution a bit, they might be helpful. Okay. One more thing is, you may not always be able to solve using one variable and a term substitution. There can be many variables and many substitutions of terms by those variables or replacing those variables simultaneously, right. So, it will be something like a set of expressions of the form x by t, right, but we can confuse with the sets, already sets are there in clauses, we will use some other notation. Instead of curly brackets let us write square brackets. So, we say that a substitution is an expression, it is really a set written in a different way of the form say x1 by t1, x2 by t2, xn by t, right. Simultaneously all these x1 to xn will be substituted by their corresponding terms t1 to tn, that is what we mean, fine. Now, where these xi's should be variables and ti's are terms, okay, and something else we want, since we want it to be simultaneously substituted. Suppose you have x by a here and also x by b there, then which one to substitute we do not know, right. So, we also assume that all these xi's are distinct, okay. So, xi's are distinct, this much at least we need, is that clear? That is how we will be tackling the substitutions now. So, suppose you have gone one step in the resolution process using the substitutions, now you see another substitution is required. So, you should be able to compose the substitutions with the earlier substitutions, right. So, first we have to study what is composition of substitutions, slowly we will be dragged to so many things because we require resolution to work, but let us see how this substitution works. Suppose I have a term t which is equal to f of x1 comma g of x2 x1, okay. I take a formula x which is say p x3 x4 x1 and then this t, fine. Suppose I take the substitution sigma equal to say x1 by a, x2 by f of x1, right. F is of two variables x1 and say x2 again, okay. Suppose we start with this. Now, let us apply this sigma on t. So, we will write that as t sigma. So, sometimes if it is readability is at some problem, we will write another bracket here for t or brackets for sigma and others, right. Sometimes we will use them. Now, let us see what is t sigma, what will it be? At a time we have to substitute all these things, that is what it means, simultaneously, not one after another, fine. So, x1 will be substituted by a, that means it will be equal to f of a, next is g of x2 will be substituted by f of x1 x2, so that is f of x1 x2, that is x2 is gone, next x1 is substituted by a, that is it. You are not supposed to write again substitute x1 and x2, that will be again t sigma of another sigma will be coming up at the right, fine. That is how we will be proceeding. So, we have x sigma. Now, x is p, x3, x4, x1. So, they are not substituted at all, they are kept as they are x4, but this x1 becomes now a and then t. Is that clear? That is how we will be proceeding. Now, for the compositions, we need compositions, right. So, let us define how composition is taking care of the replacements. So, we again give a definition, let say sigma equal to a substitution of the form x1 over s1, say there are m variables to be replaced by m terms, and say theta equal to similarly for y1 by t1, yn by tn, they can be different in number. Okay. So, we define sigma composition with theta as another of substitution. This would be a substitution that we have to check also, right. So, obtained in the following way. Well, how do you suggest? Suppose I have this theta, so I am taking it from the right side, that means here there will be t or some x on which it will be applied, right. So, that means first sigma is applied, then on that theta is applied, right. So, now suppose in sigma x has changed to a, x has changed to y, let us say. Now, in theta y has changed to a, then ultimately x should change to a, right. So, that means there will be a component in sigma which is of the form x by y, and there is a component of the form y by a in theta, right. Is that okay? So, in place of x we are going to replace y theta, right, y, and y has become changed to a again. So, theta is really applied to y, the denominator, fine. So, you must consider this set first, consider x1 by s1 theta, x2 by s2 theta, xm by sm theta. Possibly there is some change, so we first use this theta on all the denominators. Now, what happens is there can be some other y's which are not covered in x1 to xm, they should also be added, right, because on a formula, suppose this is a formula like your x3, here I apply theta where x3 is there, I do not have x1 x2 for simplicity, but x3 is there, say x3 by a. Now, that x3 by a should also be added here, otherwise it will not give me the composition. Is that okay? So, you have to add all those things. Now, add y I by t I to this set, provided y I is not equal to any of this x, right. So, that means it does not belong to x1 to xm, right. If that y is already covered here, okay, then this one would have taken care. So, I do not have to add those things, I will add only those which are already not covered x1 to xm, fine. But this need not be a substitution. After this addition of all these yi's, you have updated it. So, it is in the form x1 to xm sm by theta and then some other y's which are not x's, fine. But that need not be a substitution, because some of these things can give same variable, say x2 and s2 is our x3, x3 has become x2 in theta, then x2 by x2 is not allowed in a substitution, they should not be, they should be different, right, otherwise it is vacuous, fine. So, that vacuousness we can really deal with while defining the substitution itself. We may say no xi is equal to a ti, that ti, fine. So, you may say xi's are distinct and xi is not equal to Ti, otherwise unnecessarily you will be writing it out, which is not required. So, now we will delete all those things, delete from the updated list any substitution of the form say z by z. If they are same, just delete them. Okay. So, this deletion will be done only from this set really, not from yi's by ti's, because they are already a substitution, right. So, they will be deleted from this set, fine. Then we can update this z by z, instead of writing z by z we can write delete xi by si theta provided xi equal to si theta, right. So, let us update it. Delete from the updated list xi by si theta if xi is equal to si theta, fine. That should give us the composition of sigma and theta. Is that clear? Let us see an example how it proceeds. So, suppose I take sigma equal to, let us start with that, x by a, y by f of a, z by f of x and theta equal to y by z, x by b, z by f of a. You can add one more, say u by y. Okay. So, let us see what is sigma composed with theta. So, now for computing this, first we have to take sigma where denominators will be replaced by or is operated by theta, right. So, first we consider the list x by a theta, y by f of a theta, z by f of x theta, right. So, this is equal to a is a constant, does not matter. So, x by a remains, f of a is also a closed term, so that remains. Now, x is a variable, so x is taken to b, so this becomes z by f of b, fine. So, next what we do, add anything extra here which is not x y z, right. So, x is there, y is already there, z is there, only u is not there. So, that one only will be added. So, update it to x by a, y by f of a, z by f of b and u by y. Okay. Now, you have to delete all those things which are repetitions, x a, y f a, z f b, there is no repetition here, right. Had it been z by z, then you would have to remove it, otherwise leave it as it is. So, this is your sigma composed with theta. What about theta composed with sigma? Let us try to see what it is. So, then I have to consider first theta, denominators will be replaced by or operated over sigma. So, that gives theta as y by z sigma, x by b sigma, z by f of a sigma, u by y sigma. Okay. So, this is equal to y by z sigma, which is f of x, x by b, because b is a closed term, f is a closed term. So, f of a as it is u by y sigma. So, y sigma is f of a. Right. Now, there is nothing to be added in sigma. We have x, y, z, already we have x, y, z here. So, nothing to be added. Now, anything to be deleted? No, because no numerator is same as the denominator here. If they are same, then we have to delete it. Fine. So, that is your theta operated with sigma, composed with sigma. Are they same? No, right, they are different, because x to a, x to b, we found the difference. We can go further, but that is fine. So, we see that sigma composed with theta is not equal to theta composed with sigma. It is just like your permutations. Two permutations between, they need not commute. That is what exactly being done here also. Okay. So, what you can see is that if theta, sigma are substitutions, t x, okay, let us write one only. So, t is a term, x is a formula, then t operated with theta composed with sigma should be equal to t theta, then operated sigma. That is our purpose of defining the composition. Fine. Similarly, x theta over sigma should be equal to x theta operated over sigma. Fine. It is now convincing. How does it go? But then you need a proof. Okay. Proof is very uninteresting, because it is by induction anyway. We have nothing else. So, but induction on formulas will be easier, because you can just have induction on the number of free variables in x, right, and you can also limit all your formulas to quantifier free formulas, no problem, because that is where we will be using, but nonetheless it is true for any formula. So, you can have induction on the number of free variables over x, but then for t it is a bit difficult. Again you can have number of free variables, but that will not give any structure of t, right. So, there you may need how t is looking like, what is the pattern of t, inside how many brackets are there and so on, that is you may say on the level of the term t. Okay. So, we leave the proof here, but now you see our definition is itself mechanical, it giving a mechanical way how to proceed for the composition of substitutions. You can compose them. Our aim is to use the composition or the substitutions to do resolution process, where you may have mx and then another not dx, then you have not ma, mx and not ma should resolve, right. So, naturally you use the substitution x by a, right, on both of them, mx and not ma, use both of them same substitution x by a. So, on a there is no change, you would get ma, not ma, and they resolve now, right. That is what we are going to do. So, applying the substitutions for this resolution to work. Fine. Now, you see if you start with say mx and not ma, it is easy to see what substitution it is. Okay. Suppose you have mx and you have not ma. Now, you see that our substitution should be x by a, choice of the substitution. so that both of them will be able to resolve, right. Once this substitution is applied, this becomes M A, this remains as not M A, and they resolve. Okay. Now the thing is, they may not be that simple as one variable and one constant. There can be many terms, many variables also. Okay. So a general substitution might be required to be applied. Now how to get such a substitution? Okay. We can guess here easily, like we want to write one algorithm how mechanically we will be able to guess or get that substitution which should be applicable, right. But there is also a problem, even if you substitute, you get some way that may not be very general, right. For example, I have M of x, I have not M y, right. I can have one substitution which is x by a, y by a, right. With that itself I can go for the resolution, this becomes M A, this becomes not M A, fine. But then there is one more, I can say x by y, okay, with which I will get M y here, not M y here, they can also resolve. But I would prefer this, because by this I can have a free variable, I can use the same thing later, this whatever conclusion I get from this can be used later. But these two, if I take x by a, y by a, I can never use it, it is gone, right. So generality will be lost if I choose such a substitution. So you want a general unifier to do it, they are called the unifiers or substitutions which will keep this generality preserved till we need it, right. So this is what we want to do, fine. So for this purpose we will define again some other concept. Say from these two I would consider not Mx, not Ma, this set, okay. Then I will say that x by a unifies both the literals, right. Once I apply x by a, both of them become same, that is the concept of unifier. So a substitution is a unifier of a set of literals, or even you can say set of clauses, but let us take only literals now, if that becomes a singleton after the substitution, right. Is that okay? Now for the set of formulas you can go, there is no problem. Of course we need only literals or clauses, still you can apply for general formulas. Okay, let us say for clauses, let A be a set of clauses. So our assumption is all these clauses are in DNF, because we are using only SCNF here. So already they are disjunctive clauses, disjunction of literals. Now we say that a substitution sigma is a unifier of A if A sigma is a singleton. Okay, which means if you have A equal to say x1 up to xn, I should have x1 sigma equal to x2 sigma equal to xn sigma. If this happens, then that substitution is called a unifier of the set A, right. Sometimes we will say unifier of the clauses x1 to xn, fine. Let us see one unifier. Suppose you take x equal to, we will start with that formula, p x y f of g of z, and then the next is p u f of u f of v. So this is my set of clauses, okay. I take sigma equal to, as suggested, x by a, y by f of a, then u by a, z by a, and v by g of a. is it a unifier or not, we want to verify. Okay. So, now we see P x y f of g of z, sigma is applied over that, right. So, this is equal to P. Now, in sigma x is a, y is f of a, f is remaining as it is, g is remaining as it is, z is a. Okay. That is what it is. And then P u f of u f of v sigma. So, this is P u is a, then f a, f v is g of a, that is same. Okay. So, you see that both of them are same. Therefore, x sigma is a singleton. So, sigma is a unifier. What about x delta? So, this is x, or let us write equal to P x y f of g of z, P u f of u f of v. So, now on a set directly we are applying the substitutions. So, it means once you have a set sigma, sigma and some theta will be equal to set of all x theta such that x belongs to sigma. This is the notation we are using, fine. So, this is equal to, and we have delta. So, delta let us take x over u, y f of u, v g of z, fine. So, this is P. Now, x becomes u, y becomes f of u, f of g of, there is no z, right. So, it remains no, v is g z, x is u, y is f u. So, it remains, there is no z, and then P u as it is, f of u as it is, f of v is f of g of z, right. So, this is a singleton. Right. So, delta is also a unifier. Okay. What about theta? Let us try that also. X theta equal to, now here theta equal to what? Where let us write that theta is x over u, y f of u, v g of a. So, the difference between delta and theta is x by u is same, y by f u is same, v by g of a instead of g of z, right. So, let us see x theta is P, x is u and y is f of u, and then v is not occurring there, okay. V is not occurring there, z again same. Okay. Is it same? Huh? Here. So, here what happens? V is replaced by g of a, right. It is not a unifier, right. Second one is different now. Second one is P u is, there is no u, so remains f of u remains, f of v becomes f of g of a. right, they are not same. So, theta is not a unifier. Okay. But suppose you have z by a now in theta, then it becomes a unifier. Is that okay? So, let us have another, say tau equal to x by u, y by f of u, v by g of a, z by a. Now, let us verify whether this is also a unifier or not. Once you have z by a, so this z becomes a, that will unify. Is that clear? So, this says theta is not a unifier. Okay, but tau is a unifier of x. So, unifiers are not unique, that is clear now. We want a general one. Which one of these you would choose? Theta is not a unifier. Which one of sigma, delta, tau you would choose for a general one? Delta you would like. Yeah? Why? It keeps the variables. But we can give another mechanical way. We can say that all the other two, these are the two unifiers, can be seen as delta composed with another substitution, right? That is possible. Is it so or not? For example, let us say sigma. Is it sigma equal to delta composed with another substitution? Is it so? Let us see, sigma takes x to a, so u should be going to a, right? U has not gone anywhere, it is there. U is going to a, I can say u goes to a here also. It will be deleted anyway in the composition, fine. So, then what else? Z to a, yeah, is that all? That should. Let us find out whether it is that or not. So, now with delta, first I have to take delta and update it. So, from delta I would get x by u and this, call it something, call it alpha. So, now x by u alpha, y by f of u alpha, v by g of z alpha. I must consider this set first. Okay. Then what else I should do? I should add to it all those in alpha which are not x, y or v. None of them is x, y or v. So, both of them will be added. So, we will add to it u by a, z by a. Okay. Now, this is equal to x by u alpha, alpha is here. So, u alpha is a, y by f of u alpha, so that becomes f of a, v by g of z alpha, z also becomes a, so g of a, and u by a, z by a. Is it same as sigma? Yes, it is same as sigma, x by a, y by f of a, u by a, z by a, v by g of a, right? This is equal to sigma. So, this is correct, fine. Then we would prefer delta as our chosen unifier. Okay, we will give a name to it. Let A be a set of clauses a substitution or we can say a unifier directly. Unifier delta is called a most general unifier or let us say MGO if for each unifier sigma there exists a substitution alpha such that sigma equal to delta composed with alpha. Okay. So, delta is our chosen one. We would say we will be happy with delta, because any other time we see some unifiers we can use another substitution to get that back, fine. That is why we will choose this delta. But then most general unifiers are also not unique. Okay. Can you see that? Why they are not unique? For example, come to this x, this was your x, delta was a most general unifier, as we have seen here, we have not proved yet, right. So, now what happens? Can we choose another most general unifier? You have x by u, y by f of u, right. So, instead of this, suppose I choose u by x, y by f of x. So, ultimately in x u was figuring out, right. Now, you will not figure out, x will figure out, fine. That is also a most general unifier up to renaming of the variables, right. But there can be others non trivial also, not only renaming of variables, fine, that is also possible. So, anyway, what we have seen is most general unifiers are also not unique, but then we need one most general unifier, that is enough for us, we will continue with that. So, even if not unique, it is okay for us. Now, we have to give a procedure how to get one most general unifier, fine, and then be content with that, whatever we get from the algorithm. So, once the algorithm is used, we will say the most general unifier, because whatever that algorithm computes, that is our MGO. For others we forget, others can be renaming or some substitution can be applied on it to get them, right. So, let us see the procedure to get one most general unifier. I have a class P x y f of g of z. I have another class P u f of u f of v. Now, how do I compute a substitution which will make them same? That is what the most general unifier is. I do not want to take or replace variables by constants unnecessarily. If possible, I keep the variables as it is, right. So, what I do? I just check both of them, start scanning from the left, we are mechanizing it, right. So, you should not use any semantics or anything. Now, once I scan, I see that P and P are same, matching. I want to match them, that is all, to make them same. So, next I have x here, I have u there. So, one of them should be replaced by the other, right. Now, what our algorithm will do? It will have one as the first, another as the second, right. So, first one if it is a variable, second one is a term, that is what it will search for, then substitute x by u, variable will be substituted by the term. If the first one is a variable, then it does not want to verify whether the second one is a variable or not, but if first one is a term which is not a variable, it will try to see whether that is a variable, then that will be taken, right. So, it will give ultimately one unique, that is what. So, now I have to find or add to it my x by u, okay. This is added, but once this is added, there can be other places where x is there, it is not here fortunately, right. There are other places where x is coming, then there will be a matching problem here again, but once you apply this x by u, then all those x's have been removed, right. They are really u. When you apply this substitution, you will be getting u, not x. So, better we should not go hurry to find out the next mismatch. We should apply the substitution on the formulas, then go for the mismatch, right. So, now I have say call it theta 1, which is this. I compute x and y, let us say. So, I compute x theta 1 and I compute x y theta 1, right. So, this becomes p u y f of g of z, and this becomes p u f of u f of v. That is the effect of theta 1. There is no x there, so it is reproduced as it is. Now again I match. So already I know up to this it is matching. I do not need to match to make it efficient, but you can just write crudely match again. Now again a mismatch is occurring y, and here is a term f of u. So I take theta 2 equal to theta 1 composed with y by f of u, right. So ultimately what I have to do, this y over f of u will be applied on my earlier computed formulas, okay. So I get x theta 1, really x theta 2 this, and again y theta 2. So that means y by f of u will be applied on x theta 1, similarly on y theta 1. So apply, you get p u, y becomes f of u, then f of g of z, and y theta 2 is p u f of u f of v. Again go for matching. So p matches, u matches, f of u matches, f f matching, brackets matching, right. So g of z equal to v, right. So that means I take theta 3 equal to theta 2 composed with v by g of z. That is my most general unifier. Okay. By that time my two literals have been unified to one literal, which is p u f of u f of g of z. That is the single term. Okay. So this is basically the algorithm of computing most general unifier, right. You can write the algorithm now, but there is something you have to say in the beginning when they will not match, right. For example, we have started conveniently with p. Suppose this starts with p, this starts with q, you cannot get a unifier, because predicates cannot be made same, only variables and terms can be, right. So these types of things you have to write in the beginning. First you check for the not. If you have a whole set, for that you are computing the most general unifier. So here the set comprising two literals x comma y, there can be clauses also, fine. So now for the whole set you have to start, take any clause or any literals rather than clauses. Let us come to literals, you have to match the literals now. Now in that literals, it is a set of literals, let us say. So first thing is, if one is having not symbol, the other is not having not symbol, then unifiers do not exist, right. One is starting with not, another is not having not. So mismatch will be there, nothing can be done, right. So it is not of this and it is pu as it is, then they cannot be matching. So next thing you say, if they do not start with same predicate, then they do not match, they will never have any unifier. Now comes to predicates, that is all of them should be starting with the same predicate or starting with negation, all of them, and then predicate, fine. Then only you come for the next step for matching. Then find the first mismatch. If the mismatch is for something else, to different function symbols, then they cannot be unified. One is f of u, another is g of z, nothing can be done, right. So the mismatch should be, one is a variable, other is a term, both can be variables because variables are terms also, right. At least one of them should be variable. Then take the first variable and the other term, have this substitution, then compose, go to the next step. right, compute in loops. That is how Morse general unifier will be computed.